Hello students, in this lecture we are going to learn about the application of gray body heat transfer equation on two surface systems. Okay, so the derivation of this gray body heat transfer equation I have already demonstrated in my previous lecture. Okay, so you can find the link over here. So right now we will learn that how to apply that heat transfer equation on various systems of two surfaces. Okay, so we will recall in brief. See, this is surface 1, this is surface 2, both are gray and heat exchange is taking place, radiative heat exchange. Surface 1 has temperature T1, surface 2 T2, and surface 1 has emissivity epsilon 1 and surface 2 epsilon 2. Okay, and heat transfer is taking place. Then the net heat transfer rate is given by a formula EB1 minus EB2 upon 1 minus epsilon 1 upon A1 epsilon 1 plus 1 by A1 F12 plus 1 minus epsilon 2 upon A2 epsilon 2. Here F12 is the view factor of surface 2 with respect to surface 1, view factor or shape factor. In case you don't know about this view factor, then you must watch my lecture on the concept of view factor over here. What are EB1 and EB2? These are the emissive power of the two surfaces in case we take them as black. However, they are gray, but in case we take them as black, then the emissive powers of the two, so given by sigma T1 to the power 4, Stephen Boltzmann law, and EB2 equals to sigma T2 to the power 4. Okay. Now, in the denominator of this equation, in case I make rearrangement, okay, so I am taking out 1 by A1 common, so inside the bracket I will get this. Okay, now this A1 can go to the numerator, so ultimately I will get the heat transfer rate equation to be this formula A1 in the bracket EB1 minus EB2 upon 1 minus epsilon 1 upon epsilon 1 plus 1 by F12 plus 1 minus epsilon 2 upon epsilon 2 into A1 by A2 like this. This is our final formula of heat transfer rate. Now, suppose I apply this formula to two infinite parallel planes, two gray surfaces. These two planes are gray and they are parallel and their dimensions are infinite. So I will take unit surface area of the two planes. Okay, so in place of A1 and A2 I can keep 1. Now the view factor of surface 2 with respect to surface 1 will be 1. The reason being, whatever radiations which are emitted are captured by surface 2 entirely. So F12 will be 1. So keeping the value of F12 to be 1 and A1 and A2 also 1, taking the unit surface area, I will get this. After taking LCM and doing some mathematics, cancelling out some terms, ultimately I will get this formula. You can go through. Q is equals to EB1 minus EB2 upon 1 by epsilon 1 plus 1 by epsilon 2 plus 1. This is our final formula in case two parallel gray surfaces are there. Okay, now we will take the case that there are two concentric large cylinders of radius R1 and R2, and one cylinder, smaller cylinder, is enclosed inside the outer cylinder, and heat transfer is taking place between the outer surface of inner cylinder and inner surface of outer cylinder like this. Okay, this is our surface 1, inner cylinder as surface 1, outer as 2. So in this case also F12 will be what? It will be 1. Reason being, the inner cylinder is of convex shape. So whatever radiations which are emitted by the inner surface is captured by surface 2. So F12 will be 1. And the area values will be, we know this thing that curved surface area of a cylinder is given by 2 pi R. So for inner cylinder outer surface it is equals to A1 equals to 2 pi R1L. And outer surface inner surface area will be equals to 2 pi R2L. So keeping the values of area and F12 to be 1. So ultimately I will get this formula Q equals to 2 pi R1 inside this EB1 minus EB2 upon 1 minus epsilon 1 upon epsilon 1 plus 1 minus epsilon 2 upon epsilon 2 into R1 by R2. And here I am taking for unit length, means in place of this L I am taking unit. So this will be the heat transfer rate per unit area. Now we will take the case of a sphere is enclosed inside a big sphere, a spherical shell. So inner sphere's outer surface area is radiating and inner surface of outer shell is also radiating. So heat exchange is taking place between the two. So in this case also F12 will be 1 because inner sphere's outer surface is of convex shape. So whatever radiations which are emitted are captured by this surface 2, this inner surface of shell. Okay, so A1 and A2 will be what? The surface area of sphere is given by 4 pi R square. So in place of A1 I can write 4 pi R1 square, in place of A2 4 pi R2 square, and F12 is 1. So keeping the value, so ultimately this is the heat transfer rate equation for this case. So hope by this small you would have understood that how to apply the heat transfer equation of gray bodies in two surface systems. Thank you.